Okay, hello everyone. Good morning. And today let's continue our discussion of radiative transfer and solar energy. So just a brief review. Okay, so what we discussed last time, right? We discussed the huge potential of solar energy, right? So some mainstream technologies and some experimental kind of exploratory methods to convert solar energy into useful energy. And as I said last time, right, so one of the key challenge for solar energy conversion, right, is the low energy density. Right? Today we will continue some discussion on that. Okay, so it's just a brief review, right? We started talking about the physical essence of thermal radiation last time. Right, thermal radiation, as we discussed, right, we can understand thermal radiation as a superposition, right, of many billions and billions of small antennas, right? So it's really the result of the random motion, right? Thermal random motion of atoms, right? Electrons, right? Those small microscopic particles, right, in the material. Right, because of this, right, have a large number of random emitters, right, that's emitting electromagnetic wave, right, so that thermal radiation has some very different properties, right. That's actually also another aspect that makes thermal radiation very hard to control because it's highly random, right. So compared to, for example, LEDs or lasers, right, as we discussed last time, right. So the first feature, right, is that thermal radiation is spectral, right. Which means it contains a wide range of different wavelengths of electromagnetic wave, right? Sometimes we say that thermal radiation is broadband, right? Contains a large, right, range of wavelength, right? So typically, right, the physical picture I usually visualize thermal radiation, right? We will quantify this in a minute, actually later today, right? So if you draw, right, the emissive power, which means how much energy, right, is being transferred for each given wavelength, right? It's called this wavelength dependent power, right? Wavelength dependent power. Right, typically the thermal radiation has a broad spectrum, right? But the shape of the spectrum is not random, right? So it usually has a well-defined shape, but it does contain a large range of wavelengths, right? So it typically would peak, right, at one wavelength, and it's called lambda max. Okay, so this shape of this curve is given by Planck's black body law, black body radiation law, right, which we will discuss in detail just in a minute. Black body radiation law. Okay, so the second feature, right, again, because of the randomness, right, of thermal radiation, right, thermal radiation is also, we call it directional. Right, so thermal radiation comes in a wide range of directions. Right, so basically, if you have like a small emitter, right, if this is your emitter, right, you would expect the thermal radiation to go to all the directions, right? Because this is really a random motion, right, of atoms. You can control, right, the directionality a little bit with the material properties, which we will discuss later. But in general, it's pretty hard, right? Because again, because of the randomness. Okay, the directionality of thermal radiation would be described by the so-called Lambert's law, which we will probably talk about next week. Okay, this is kind of like a preview. And the third property, right, because thermal radiation is a result of the thermal random motion, right, of microscopic particles, right? Their random motion basically obeys thermodynamics, right? So everything, so temperature plays a very important role, right? Temperature determines a few things, right? The first one is the frequency, right? And frequency and wavelengths, of course, they are directly related, and it also determines the intensity, right? How much power, how much energy the thermal radiation carries, right? Of course, just intuitively, right? You imagine like a hotter object, it's going to emit more power. Okay, so on this side, right, there are a few laws. I will just briefly talk about here. We'll also come back later, right? So for those of you who's taken 151B, right? So this should be familiar to you, right? If you haven't, if this is the first time you see these laws, right? They're actually pretty straightforward to understand, right? So the first important law is Wheelen's law, right? Wheelen's law states that basically tells you that this lambda max here, right? So as I said, right, for each thermal radiation spectrum, right, you will have kind of a maximum wavelength, right, that carries the most power, right, for a given emitter at a given temperature, right? So there's a simple relation between lambda max, right, times the temperature of the emitter, right? So the product of the two, right, equals a constant, right, equals 2898 micrometer Kelvin, right? A few examples, right? First of all, if you look at this law, right, so because lambda max times T equals constant, which means if you have higher temperature emitter, right, so basically the lambda max is going to shift towards shorter wavelength, right? So, for example, right, for this class, of course, the most important emitter is the sun, right? So the surface temperature of the sun is about 5,800 Kelvin, right? Very hot, right? Because of the nuclear fusion reactions happening inside the sun, right? So if you do the calculation, right, so the lambda max, right, for the sun is about 500 nanometers. Okay, so 500 nanometer, right? If you look at the EM spectrum we drew last time, right? So right, from 400 nanometer, right, to 700 nanometer is the visible range, and this is the visible, right? So 500 nanometer is kind of in the middle of the visible range, right? So actually at 500 nanometer, right? So it's kind of it's actually in the green color, right? So the solar radiation coming in, right, from the sun, it's largely visible, and its peak is at a green color, right? So which happens to be, right, the color that our eyes are most sensitive to, right? So this is the result of millions of years of evolution, right? So our eyes kind of adapt, right, to the incoming solar radiation. Okay. Right, again, if you have any questions at any time, right, so you just unmute yourself and just feel free to interrupt me and ask questions, okay? Right, because when I'm just talking to the slides, I feel like I'm going very quickly, okay? So I prefer a slightly slower pace. Okay, anyways, this is for the sun, right? So for the another very important object is of course the Earth, right? Or any body, right? Anything on the Earth, right? Because then our temperature is kind of similar, right? Let's say 300 Kelvin, right? Room temperature, right? If you do the calculation, right? Lambda peak, right? In this case is about 10 micrometers. Right, so 10 micrometer, right, of course, is far beyond the visible range, right? This is in the infrared, right? Again, right, so all the thermal emission we emit, right, so we cannot see, right, because it's outside the visible range, right? Okay, a third example I always like to talk about is the universe, right, the outer space. Right, we actually define the temperature, right, for the outer space because you will think that there's nothing there, right, nothing in the universe, in outer space, right? So how can we even talk about the temperature, right? Actually, the outer space is filled with radiation, right? The outer space is filled with electromagnetic waves, and you can measure the spectrum with the antenna, and you can deduce, right, what's the temperature, right? Basically, you measure what's the peak wavelength of this radiation, right? It turns out, right, you actually define the temperature of the universe or of the outer space this way, right? So it's about 2.7 Kelvin, right? So very, very low temperature. And in this case, lambda max, right, if you do the calculation, is about 1 millimeter, right, very long, right? So this is in the microwave range, but it's still a form of thermal radiation, right? It's actually the residue of the Big Bang, right, from the start of the universe, right? So after everything expands and cools down, right, this is the background that's left behind, right? So it's a 2.7 Kelvin background, right? So this has a name, right? It's called the cosmic microwave background, or CMB, right? So, and this is, people got Nobel Prize, right? Nobel Prize in physics for discovering this, right? Nobel Prize in physics, 1978, right? So basically, you can actually measure, pick up this cosmic microwave background just using an antenna, right? Because it's in the microwave range. Okay, so this is first law we want to discuss. Very important, very simple, but very important to understand many things. And another example I like to talk about is this so-called red hot, right? So if you heat up something to really high temperature, right, this object starts to kind of glow, right? For example, like the molten metal or molten iron, right? You sometimes you see in steel factories, probably on the TV, right? You can see the molten metal always glows, right? Kind of reddish color, right? So that's because when you heat up something to really high temperature, right, its thermal emission shifts, right, into the visible range, and then you start to see kind of reddish color, right? That means you can estimate what temperature that is, right? So that means probably the object has been heated up to maybe 1,000 or higher degrees. Okay. Okay, this is Wien's law. Right, so this is one example of how temperature determines the wavelength or frequency, right, of the radiation. Right, it determines the peak wavelength, like the maximum wavelength of radiation. Okay, a second law, right, very important, and by Stefan Boltzmann law. Right, so this law is about the intensity, right? It's about how much energy you can emit, right? So this is a law for a black body, right, which we will precisely define later today. Right? But for now, it's enough to know that, okay, so the energy, right, emitted, energy density, right, or another terminology, you can just say the heat flux, right, emitted, right, by an emitter. Right, so this is actually, it's actually for a black body, but for now, let's just think of it as any emitter, right? So let's use the symbol E, right, equals a constant, right, times temperature to the force power. Right? This quantity, right, is a heat flux, right? So it has the unit of watt per meter square, right? So how much energy is being emitted, right, per unit area, okay? Power per area, okay? Sigma is sigma, right, is Stefan Boltzmann constant. Right, so sigma equals 5.678, right? 5.67 times 10 to the minus 8 watt per meter square per Kelvin horsepower, right? So this is how I remember this number, right? 5.678, right? So as you can see, the power, the radiation, right? So the power of thermal radiation really strongly depends on temperature, right? Depends on the temperature to the fourth power, right? So it scales very fast with temperature. The Stefan Boltzmann constant is small, right? So when temperature is low, right? When, let's say if it's room temperature, right? Usually this contribution is pretty small, compared to other heat transfer channels. But if you go to really, really high temperature, say hundreds of degrees or 1,000 degrees, right, radiation usually dominates, right, because of this very strong T to the force power dependence. Okay, so these two are very simple laws we can directly apply to understand a lot of problems or scenarios with thermal radiation. So now let's look at one example, right? We're still kind of in the introductory phase, right, of radiation and solar energy, right? So let's look at solar radiation. Let's apply the laws here, right, to solar radiation, right? To some of you, this may look familiar, right? This is kind of one of the homework problems you did for 151B, but I think it's good to to kind of review this problem a little bit, right? This helps us understand how we can calculate the amount of energy that we receive from the sun, right, on Earth. Okay, let's look at solar radiation, right? So let's say this is Earth, right? This is Earth. This is where we are, right? Earth. We know the size, right? So the radius of Earth is 6.371 times 10 to the 6 meter, right? It's about 6,000 kilometers radius of Earth. Okay, and the sun is very far away, right? This is the sun. Right? Sun is of course much larger, right? So this is not drawn to scale, of course. So the radius of the sun, right, is about 6.96 times 10 to the 8. Right, it's about 2 orders of magnitude larger than Earth, right? So we know the sun, right, has a temperature, surface temperature about 5,800 Kelvin, right? More precisely, equals 5777 Kelvin. Okay, and of course, the sun is very far away from the Earth, right? So there's distance, right? The distance between the sun and the Earth, right, is about 1.496 times 10 to the 11th meter. Okay, so now let's first apply Stefan Boltzmann law, right, to figure out what's the total amount of power, right, thermal radiation, right, emitted from the sun. Right, we can calculate total emitted power from the sun, right? So if we, for now, we approximate, right, the sun is a black body, right? Let's call this QS, right? The heat, total amount of heat or total amount of energy, right, emitted from the sun, right? We use Stefan Boltzmann law, right? Stefan Boltzmann law is energy per area, right? So basically what we need is the surface area of the sun, right? 4 pi RS square, right? The surface area, right, times Stefan Boltzmann law, sigma T sun to the force power. Okay, if you do the calculation, right, this is a huge number, again, because the, of course, because the sun is large, right, it's huge, and also because the temperature is very high, right? If we go to force power, right, it's very strong dependence, right? So this gives you about 3.84 times 10 to the 26 watt, right? So this is a huge, huge amount of power. I remember the power we consume on Earth every year is about tens of terawatt. A terawatt is 10 to the 12. So this is 10 to the 26, right? This is astronomical number, right? Very large. But unfortunately, not only a tiny, tiny fraction of this power, right, would reach the Earth, right? So this, again, has to do with the directionality of thermal radiation, right? As I said, thermal radiation is a highly random process, right? So the radiation emitted from the sun actually goes just uniformly, right, towards all the directions, all the possible directions, right? So it goes to all the directions, right, towards the space, right? So because the Earth is so far away from the sun, right, only a tiny, tiny fraction, right, would arrive on Earth, right? So the way to think about this problem, right, you can draw a large spherical surface surrounding the sun, right, with the radius being the distance between the Earth and the Sun, right? So you can draw like a very large, right, spherical surface around the Sun, right? So you can think of the energy emitted from the Sun, right, would be uniformly distributed, right, on this spherical shell, right? Because Earth only intersects this spherical shell, right? Tiny fraction of this spherical shell, right? So the Earth would only would only receive a very low power density from the Sun. And this is an idea, right? But let's do the calculation, right? Solar radiation intercepted, right, by the Earth. Okay, right? So we have this total amount of energy, right, being emitted from the Sun, right? So when it arrives on Earth, right, we can think of this amount of energy has been diluted, right, by the large surface area of a huge spherical shell, right, surrounding the Sun, right, whose radius is the distance between the Earth and the Sun. Right? So the heat flux, right, we see on Earth, right, Q, it's called Q solar, right? This is heat flux on Earth, right? So we can calculate this, right? Equals the total amount of energy emitted from the Sun, right? Normalized by the surface area of this large, right, spherical shell, right? The radius here is L. L is the distance between Earth and the Sun, right? We do the calculation, right? So this will dilute, right? Because L is very large, right? So this will dilute this power down a very large factor, right? So what you get is about 1.3, right, 64 watt per meter square, right? So this is the solar heat flux, solar energy flux we receive right on the top of the atmosphere, right? So this is the amount of energy that arrives on Earth, right? So this number is a well-known number, right? It's called the solar constant, or sometimes we also call it insolation. Right, so this number basically gives us the upper limit, right? What we can do with solar energy, because this is the amount of energy, solar energy that arrives on top of the Earth's atmosphere. And so we cannot, unless one day we have some technology in the space, right? Then we can think of better ways to harvest solar energy, right? There's one concept proposed by the theoretical physicist Freeman Dyson, right? He recently passed away. It's called the Dyson sphere, right? He said, okay, if we can someday, if you can develop like an energy harvesting sphere that surrounds the Sun, right? We can suck all the Sun energy and use it, right? But that's kind of a sci-fi concept, right? But so basically on Earth, right, this is the heat flux we have to deal with, right? Another anecdote is that there was a company when I was a PhD student in Boston, right? So there was a company in Cambridge, Massachusetts, called 1366, right? So basically they derived their name from this, right? They are a solar cell substrate fabrication company, right? But somehow they missed the solar constant. I think I did the calculation. I think it's 1367, and it's consistent with almost all the literature. But they call them 1366. I don't know whether their company still exists, but this is where their name comes from. Okay, so this again, right, I emphasize this is not the solar flux we receive on the ground, right? So it's not at Santa Barbara. I think we only receive a fraction of this energy flux, right? This is on top of the atmosphere, right? But this can be measured, right? Can be directly measured, right? By satellites, for example. Right above the atmosphere, right? Okay, we have the number, but we don't really have a good feeling like how large or how small this is, right? Just to give you a feeling, right, why this energy flux is so hard to convert, right? So this is actually, right, if you think about the cell phone CPU, right, energy consumption, typical, right, typical, a cell phone CPU, right, if you look at your cell phone, right, when your cell phone gets hot, right, so the amount of heat dissipated by your cell phone is actually about 10 to the fourth, right, watt per meter square, or you can use 1 watt per centimeter square. Right? This is the common unit used, right? So as you can see, right, the solar flux arriving on Earth is actually 1/10, right, of the energy dissipated, right, from your cell phone CPU, right? So the cell phone CPU is already, right, you don't really feel anything, right? So usually it can get hot, right, but not too much, right? So if with this, right, so the solar heat flux is only 1/10 of that heat generated in your cell phone, right? So that's why this is actually very, very low energy flux, right? So that's why it's very hard, right? Very hard to convert this flux efficiently into useful energy, right? Typically, we need to do concentration, and we need to concentrate solar radiation using optics, for example, right, to boost the energy flux so that we can conveniently, right, more conveniently convert with a higher efficiency. Okay, so this is the heat flux, right? This is the heat flux energy per area, right? Received, arrives on Earth. We can also calculate what's the total amount of solar power, right? Intercepted, right? Total, right? Solar power, right? Intercepted by Earth, right? This is going to give you the number, right? I showed last time, right, on the first slide, right? So the potential of solar power. Right, let's say this is from the sun to Earth, right? So again, because this solar energy is uniformly distributed, right, on this large spherical shell, right? So the Earth only intercepts a small fraction, right, of this spherical shell, right? The fraction that the Earth intercepts actually is determined by the cross-sectional area, right? So if you look at I don't know whether you can see, right? So it's actually the fraction, it's the cross-section area of the Earth that's intercepting, right, the incoming solar radiation, right? So we can use then the cross-section area, right, QRE square, right, instead of the surface area of the Earth, right, times Q solar, right, because not all the surface area of the Earth is receiving solar radiation, right? For example, the back of the Earth, where it's night, right? So there's no radiation coming in, right? So if we do the calculation, right, this is about 1.6474 times 10 to the 17th watt, right? Or equals 174,000, right, terawatt, right? So this number is still larger, right, than what we showed last time, right? Again, because this is the power arriving on top at the top, above atmosphere, right? So we will discuss in a minute, right, what happens when the solar radiation passes through the atmosphere, right? We actually have further loss. Before that, right? So let's any questions so far on this simple application of the few laws we introduced so far, right, to the solar energy scenario. Okay, another important concept here is the solar angle. Right, so this is, again, this has to do with, right, the directionality of thermal radiation. Right, solar angle is, if you imagine, right, you stand on the surface of the Earth, right, so you look at all the directions, right, the solar radiation comes in, right. So let's say we are standing here. Right, so let's plot this. Let's say we are standing somewhere here on Earth. Right, I don't know whether you can see my pen here. Right, so basically, if I stand here, right, I measure like what's the incoming angle of the solar radiation, right, towards this point, right. So basically, I basically look at the sun, right. So right? So, so this is the angle range, right? I will receive solar radiation, right? Because the sun is huge, but because the sun is so far away, right? So the angle of solar radiation coming in, right, would only vary from this, right, to this. Right? As you can see, it's very hard, even very hard to draw them differently, right? So we can actually estimate, right, what's the angle, right? So the solar angle, right, is called theta s, right? So this is approximately, right, the 2 times the diameter of the sun, right, divided by the distance, right, between the sun and the earth, right? Basically, we're talking about this angle here, theta s. Okay, so if you look at the incoming solar radiation, okay, so this is if you do the calculation, right, again, because L is very large, right? So this is a very small angle, right? It's about 9.3 milliradian, right? So this is you can convert this, right, into degrees, right? This is about 0.53 degrees, right? Very small, right? So this tells us that right? So this angle is basically 0, right? So basically, if the angle is 0, right, which means the solar radiation comes in parallel, right? So direct sunlight, right, comes in, right, approximately, right, as parallel rays. Okay. Okay, so this is a very important factor to consider, right, when we design solar energy conversion devices, right? So, but I emphasize here, this is the direct sunlight, right? So later we will discuss there are other diffuse sunlight, right? When the light passes through the atmosphere, right? Some of the light is gonna be scattered, right, and become diffused. Okay, so this is because this is purely a geometric effect, right? Because the sun is so far away from the Earth. Okay, very good. Right, so let's continue. Right, so now we have the solar flux, right? The energy, solar energy on top of atmosphere, right? Then we look at what happens, right, when the solar energy, right, penetrates the atmosphere. Okay, so let's look at solar radiation, right, interaction with atmosphere. Right, we will introduce a few material properties, right? We will discuss later, right? So this is Earth. Right, so now we can draw this slightly larger. Right, and then we have the atmosphere, right? The Earth is surrounded by atmosphere, a thick layer of air, right? So then the solar radiation comes in, right? As I said, right? So approximately you can think of the solar radiation come in, right, as parallel rays because of the small solar angle. Okay, the Earth, of course, itself is also emitting, right, some thermal radiation, but this is a very small amount, right, compared to the incoming solar radiation. Right, turns out what happens is that not all the solar radiation on top of the atmosphere can reach the ground, right? So about part of this incoming radiation would be reflected, right? Reflected. Okay, so it's actually about 33%. Okay, so this gives us one concept, right, which is the reflectance. Right, we will discuss these few concepts extensively later, right, in the class, especially for materials, right, used in devices, right. So the reflectance tells you how much of the energy, right, of the incoming energy is reflected back, right, or into other directions that not even enters, right, the atmosphere, right. In this case, is about 33%. Okay, so then part of the radiation is going to enter, right, the rest of the radiation is going to enter the atmosphere, right? But when they travel in the atmosphere, they're going to interact, right, with the gas molecules, with water vapor molecules, for example, CO2, right, nitrogen, oxygen, right? So then these gas molecules actually can absorb, right, the incoming solar radiation, right? So the solar radiation is going to be further reduced, right, due to absorption, right? So absorption, absorbed, right, in the atmosphere. Right, so in this case, it's about 22%, right? So this is called absorptance, right, of the atmosphere, right? We use the symbol alpha. Okay, so then the rest of the radiation can actually pass through the atmosphere and reach the Earth's surface, right? So then the rest transmitted, right? Transmitted. Right, so we have actually 45%, right, transmitted across through the atmosphere, right? So we use the property transmittance, right, or tau, right, to describe this material property. Okay, so now you have from previous discussion, right, we have this amount of energy, right, we receive on Earth, but only about half of this energy can reach the surface of the Earth, right? So then another calculation you can do is to calculate the land area, right, the fraction of the land area on Earth compared to ocean, right, where it's hard to set up solar plants. Then if you do that calculation, right, you're gonna end up with this 23,000 terawatt available solar energy we discussed last time, right? So, okay, but the purpose for me to talk about these concepts, right, is because I think it's a good place to introduce these concepts, right? From energy conservation, of course, we have rho plus alpha, right, plus tau must equal 1, right? So this is energy conservation. Okay. Some more terminologies, right? If tau equals 0, right, for some materials, if tau equals 0, right, then we call this material opaque, right? Opaque, right? So basically, no radiation can penetrate, right, through the material. As we will discuss later, right? So these concepts are all relative, right? So there's no absolute opaque material, right? It really depends on the optical properties of your material and how thick your material is, right? So some other scenarios, right? If there is no absorption, right? If alpha equals 0, right? We call this material transparent. Right? Again, there's no absolute definition, right? So if you make any material thin enough, right, it's going to become transparent. For example, okay, so it depends on the thickness of the material, also depends on the material properties, right, which we will discuss extensively later in the class, right? Okay, so in addition to reflection, absorption, and transmission, right, these three channels are, of course, very important, right? There is actually a fourth process that happens in the process that's also very, very important, right? It's called, as I alluded to a minute ago, right? It's called scattering. Right, scattering is, right, if you think about the gas molecules, the particles, right, some small particles in the atmosphere, right, small particle, right, when the radiation comes in, right, the radiation is not necessarily going to be reflected or absorbed by this particle, but this particle is kind of like a defect, right, like a obstacle, right, in the path of the radiation, right? What it does is it can scatter, right? So it can change the direction of the travel direction of the incoming radiation, right? So after interaction with this particle, right, your radiation is gonna go into different directions, right, with different intensity, right? So this is, right, so this is basically a change of travel directions, right, due to small particles or objects. Okay, so right, so there are a few scenarios, right? So we can use this simple principle to understand a lot of natural phenomena, right? One thing is why the sky is blue, right? Why the sky light, right? The sky background is blue, right? This is because, right, if you have a clear day, right? So then the particles, right, in air are, they are all very small, right? There's no droplets, for example, if it starts to rain, for example, right? So if the scatterer, right, the small particles, if the scatterer size, right, is much smaller than the wavelengths, right, of the radiation, right? In the case of solar radiation, it's 500 nanometers, right? If you have particles, dusts, dirts, right, that's in the atmosphere, or gas molecules, right? That's very, very small, much smaller than the wavelengths of solar radiation, right? So then the probability of scattering, right? So the chance, basically, right? How high is the chance that the incoming radiation is going to be scattered by this small object, right? Actually, scales of scattering, right? Scales as, right, the frequency to the force power of the radiation, or, right, inversely, 1 over wavelengths to the force power, right? So this scenario is called the Rayleigh scattering, right? So this means that the shorter wavelength, right, shorter wavelength radiation, right, shorter wavelength radiation, right, in this case, blue and purple, right, in the solar spectrum, right, is much stronger, much more strongly scattered, right? It's much scattered, right? By, again, right, if it's a clear day, right, the particles in the atmosphere, they are very small, right? So the incoming direct sunlight is going to be scattered into all other directions, right? So that forms the background, the skylight background, right? That's blue, right? That's why in a clear sky you have, right? This is why the clear sky is blue. Okay, so now you have a cloud, right? Of course, you know the cloud is white, right? So that's because what forms a cloud, right? What forms a cloud is actually the water droplets, right? So so they have actually a larger size, right? So if the scatterer size, right, becomes larger and becomes comparable, right, to the wavelength of radiation, right? For example, right, water droplets, okay, in a cloud, right? So then we are in a different regime, right? This regime is called ME scattering, right? So basically, we will have more broadband, right? More broadband scattering, right? So basically, a wide spectrum of the incoming light would be scattered, right, by the particles, right? That's why we will have white cloud, right? Then you can ask, okay, what happens, right, when you have a dark cloud, right? That's when your particles becomes even larger, right? It's already about to rain, right? So then the solar radiation really can barely penetrate, right, the cloud, right? So you really don't see much solar radiation passing through the cloud anymore, right? So that's why you have dark cloud. I mean, the particles size are even larger. Okay, so this is just something to keep in mind, right? So because of this, because of all these scatters, right? So the right picture, the correct physical picture of solar radiation coming into Earth, right, is right. If this is the ground, right, this is the sun, right, this is on Earth, right. So you always, when you think about solar energy, right, you think about converting solar energy, right, there are always two components, right, that need to be considered, right. That also kind of is one of the challenges, right, it's associated with solar energy, right. So one part is the direct sunlight, right. This part of the sunlight is relatively well behaved, right, because as I said, right, it's approximately parallel, right, so coming from one direction, but of course depends on the position of the sun during the day. But in the meantime, right, you will have scattered, right? So this is direct sunlight, right? This is a direct sunlight, right? Now, because of the existence of the scattering events, right? A large number of scattering events, right? You also have diffuse, so-called diffuse sunlight, right? That comes in from all other directions, right? This is because the scattering events, right, in the atmosphere. Okay. Right, of course, typically, right, the diffuse sunlight, at least on a clear day, right, the diffuse sunlight is much weaker compared to the direct sunlight. Right? This part is the diffuse sunlight. Okay, so now if you design your device, right, your solar conversion device, of course, the easiest way to do is to optimize your device to the direct sunlight, right? So then your device would work very well on a clear day, right? But then if the weather changes, right? So when the diffuse sunlight becomes more important, then you have to consider how to also optimize your device for that, right? So that's one challenge is actually associated with solar energy utilization. All right. So another very important phenomena I want to introduce, right, to that's associated with atmosphere, right, is selective transmission of the atmosphere. Right. Basically, if you look at the atmosphere, right, it's not the same, right, to different wavelengths of radiation, right? Its transmission can be higher for a certain range of radiation, right? It's basically in short, right, the feature of this atmosphere surrounding the Earth is that it actually, right, Earth atmosphere, right, it has absorbing gas, right, has absorbing gas, right, for infrared wavelengths. Right, the most notorious one is CO2, right, carbon dioxide, because its peak absorption, right, is at 10 micrometer. Right, later we will discuss, right, how do we understand absorption of these molecules, but for now we just take it as a fact, right? So the carbon dioxide in the atmosphere, right, they tend to absorb, right, longer wavelengths infrared thermal radiation, right, in the range of 10 to 15 micrometers. Right, it's notorious because if you remember, right, the thermal radiation from the Earth's surface, right, the peak wavelength is about 10 micrometers. Basically, the CO2, right, in the atmosphere is going to very strongly absorb, right, the radiation emitted from the Earth. But there are some other gases, like ozone, right? It absorbs about also around 10 micrometers. But ozone is very good, but because it also absorbs UV, right, 260 nanometer, very short wavelength UV light, right? So the ozone layer is kind of like a filter, right? So it filters out a large portion of the UV light from the sun, right? That protects us because the UV light can be harmful for the health, right, of the lives on Earth, right? So then another important component, of course, is water vapor. Right? Water vapor absorbs about a few microns, right? So there is a strong peak around 6.3 micrometers, right? So then if you look at this, basically what happens, right? So if you, again, right, recall what we discussed, right, the spectral properties of thermal radiation associated with different objects with different temperature, right? If you look at the solar radiation, that because the sun is much, much hotter, right? The sun is about 5,800 Kelvin degree, right? So the solar spectrum, incoming spectrum towards Earth, right? This is the solar, right? Peaks around 500 nanometer, right? So the Earth's atmosphere is basically transparent, right, to the incoming, so relatively transparent to the incoming solar radiation, right? The transmittance is 45%, right? About half of the solar spectrum can transmit, right, through the atmosphere, right? So then there's also, as I said, right, the Earth itself also emits thermal radiation, right? The Earth, right? Because Earth is at about 300 Kelvin, right? So the peak wavelength is about 10 micrometers, right? Now, if we have the increasing content of concentration of carbon dioxide in the atmosphere, right? So then this carbon dioxide layer is basically a selective kind of thermal insulation layer, right? So it lets the solar radiation in, but it will absorb, right, the emission from the Earth and emit it back to Earth, right? So this creates this so-called greenhouse effect. Right, so that's why, right, so the increasing level of CO2 is especially bad, right? So it's gonna cause the global warming and some climate change effect, right? So as you can see, we can also understand, right, these effects from the perspectives of thermal radiation. It's basically the radiative properties of the Earth's atmosphere, right, that creates this greenhouse effect. Right? So now we have, basically now we have the radiation emitted from the sun, right, travels through space and through the atmosphere and reaches the the Earth's surface, right? Then let's look at maybe a very simple solar conversion device, right? So basically I'm mapping out the whole process for you, right? The solar energy conversion, right? Let's look at the simple solar energy conversion device on Earth, right? Let's just look at like what factors, right, are important, right, in the device design, from the device design point of view, right? So let's think about just a very simple solar hot water system, right? So this is very commonly found nowadays, right, in a lot of developing countries, right? So let's say if you have just very simple design, sorry, right? We have, this is a device, right? So usually, right, you have a window. And this is a glass window to let the solar radiation in, right? Right. So a large portion of the device is just thermal insulation, right? You want to minimize energy loss, right, from your device, right? Because you're using the solar heat, right? So now the radiation, right? Then you have like a glass window, let's say, right? Then you have right inside your device, right? Typically, you will have an absorber, right? So right, so this is absorber, right? Then you run some water, right? Water pipes, right? Inside your device, right? Water, right? Basically, you want to use, right? The incoming, this is the solar radiation, right? You have incoming solar radiation, right? So then, because you have a glass window, right? So only part of the fraction of the solar radiation can actually enter your device, right? So, right. So then this solar radiation that goes into the device is going to be absorbed, right, by this absorber, right? Of course, you want your absorber to be as efficient as possible, right? So you can heat up your absorber, right? Then you can use the absorber, right, to heat up running water, and you get hot running water. Right. So now we have some knowledge about solar radiation, right? Then the question is, what are the factors, right, how we can optimize this device, right? So for example, first step, right, if you design your glass window, if you have a simple glass window, right, we will discuss later, right? If you just have a simple glass window, you don't do anything to it, right, then part of the radiation is going to be reflected, right, by your glass window, then you lose this fractional energy, right? So basically what you want to do, you want to minimize, right, reflection. Right, so one thing you can do is by using a so-called anti-reflection coating. Right, so basically through some smart optical design, right, you can actually minimize this part of energy loss, right? So you can minimize the reflection, right, from any material surface, right? This is an important topic we will discuss later in the class. Right, for the absorber, right, how can you maximize the efficiency of the absorber, right? So as we will discuss in a minute, right, for any absorber, right, that you use to absorb the solar radiation and heats up, it also, right, itself also emits thermal radiation, right? So if itself emits thermal radiation, that will create energy loss for you, right? Because you don't want energy loss from your absorber, right? So you want this absorber to hold energy as well as possible, right? So one thing you can do, you can design a selective, so-called selective absorber. Right, a selective absorber, basically, it's a very good absorber for the solar spectrum, right? For shorter wavelengths. It absorbs everything, but then it doesn't really emit much, right, in the IR range, right? You would say, okay, how is that possible, right? It sounds like it's gonna violate second law of thermodynamics, right? So that's very good intuition, but I will discuss, right, maybe next week, right, we will introduce how we can design selective absorbers, right, to maximize the efficiency of the absorbers. Right, of course, you have thermal insulation, right? You want your thermal insulation to be very good, right? Typically, you also have vacuum, right? So to minimize convection loss, right? So okay, these are just a few kind of a preview, right, of some important device concepts, right? We will discuss later in the class. Okay, so I think this example, right, this is a very long example, right? But the purpose of this example is really to give us a map, right? So I always, for any of my class, I'd like to give you a map, right, first, in case you feel lost at some point, right? So where we are going, right? So this class, right, for this class, right, so we are exactly following this whole workflow, right, radiative transfer and device design for energy conversion, right? So the first part of the class, we will discuss radiative transfer and we pretend, right, we already know all the properties, right, with known material and surface properties. Right, let's say we already know the reflectance, we already know the absorptance, we already know the transmittance, right? Then how do we calculate, right? How do we understand radiative transfer, right, between different objects and surfaces, right? That's the first part of the class, right? Again, this will be kind of a review, right, for many of you. But then after that, we're gonna talk about some new material, right? So the second part of the class, right, we're gonna talk about how to, right, understand calculate and engineer right radiative properties of materials, right? So basically we need to understand the physics behind, right, the reflectance, the transmittance, and the absorptance, right? How we can calculate them given a new material, for example, and how can we engineer them, right? How can we change them, right? Mostly through kind of surface treatment, surface engineering, right? And the third part of the class, right, then we're gonna dive into really practical, more practical aspects, right? We're gonna talk about device analysis and some research frontiers. Right, with kind of the foundation, right, from the first two parts of the class. Okay, very good. Is there any question, comments so far? Very good. So let's right, this is the end of the introduction. It's kind of introduction, right, to this class, and we're gonna start our discussion formally. All right, so all right, the first concept I want to discuss is a black body, right? So this is always the starting point, right, to understand thermal radiation, right? A black body, right, by its name, right, you know it's ideal absorber. It's an ideal absorber, right? So basically all incident radiation is absorbed, right? So then it's black, right? So if any object, if you have a black surface, right, it looks black because it absorbs all the visible radiation, right, um, onto the surface, right? So you don't see any reflection from the surface, right? So then it looks black. But in this case, the black body, right, is very important. Is this is not only for visibly black surface, right? So this is for all incident, right? All incident, right? So this means all wavelengths and direction, right? So in reality, right, there is no real black body. Right? This is a highly idealized object, right? So so it's convenient for theoretical studies, but for practical reasons, right, we can approximate some surfaces, some objects to be a black body for a specific spectrum, right? For example, as I said, right, any black surface, right, we can approximately think the black surface is a black body for the visible spectrum, right? So this means, right, this implies that, right, if you have a black body, right, the reflectance is zero, right, nothing is reflected from the surface, right? How transmittance is zero, where nothing transmits through this object, right? The absorptance is one, right? Because everything is absorbed. Anything incident on the surface is absorbed, right? So this is again a highly idealized concept, right? But very important corollary, right? So is that, right, if you have a black body, right, a black body is an ideal absorber, right, but anything with a finite temperature is going to emit thermal radiation itself, right? So all black bodies also emit thermal radiation, right? So black body is actually also ideal emitter, right? So what do I mean by ideal, right, emitter, right? Ideal absorber is very easy to understand, right? It absorbs everything. An ideal emitter actually means a black body, right, emits a maximum, right, amount of energy, right, than any other body or object, right, at the same temperature, right? This is very important. At the same temperature, right? Because radiation is highly temperature dependent, right? If you have two objects with the same temperature, right? One of them is a black body, then it will emit more energy, right, than the other body, right? This is the definition of being an ideal emitter, right? Let's just give a very simple proof, right? So in case you don't believe it, right? So let's say if you have two objects, right? Two surfaces, right? One of them is black, right? And at temperature T, right, the other surface is not non-black. Yeah, it's not a black surface, right? It also at temperature T, right? So they are at the same temperature, right? Because it's non-black, then there must be some finite reflection, right? So rho, the reflectance is not zero, right? By definition, right, if it's black, everything is absorbed, right? If it's non-black, then a fraction of the incoming radiation is going to be reflected. Okay, so let's say this black surface is emitting energy flux of E1, right? This non-black surface is emitting a thermal radiation E2, right? So, so for E2 emitted by the non-black surface, when it arrives on the black surface, everything is going to be absorbed, right? But for E1, right, that's emitted from the black surface, right? When it arrives on the non-black surface, then the fraction of it would actually be reflected, right? So this part is rho E1. Okay. So now, because the two surfaces are at the same temperature, right? Because they are the same temperature from second law of thermodynamics, we know that there cannot be net energy exchange, right? Between, let's call this surface 1, this surface 2, right? Between 1 and 2 must be 0. And this is the second law of thermodynamics, right? You have two isothermal bodies, right? They cannot exchange any net amount of energy, right? So this means if you draw any fictional interface in between, right? You just count how much energy goes from left to right, how much energy goes from right to left, right? Then you must have, right, E1, right, equals rho E2 plus E1, because E1 is the only thing goes from right to left, right? There's no reflection from the black surface, right? But there you have a fraction of E1 reflected back from 2 plus the emission from the surface, the second surface itself, right? So then you must have this equality, right? So in this case, right, if rho is greater than 0, right, if the second surface is non-black, right, so then you must have, right, E1 plus E2. Okay, so basically, if you have a black surface, right, must emit it's ideal absorber, but in the same time, it's ideal emitter, right? So that's kind of another challenge, right, for solar design, right? As I mentioned, right, if you want to have absorber, you want to design an absorber to absorb as much solar energy as possible. You have to pay a price, right? There's no free lunch, right? Again, this is determined by the second law of thermodynamics, right? If you have a really, really good absorber, right, typically it also emits, right, a lot energy, right? So then you lose a lot of energy in the process, right? So how do you get around this, right? So that's actually one topic we will discuss later. Okay, it's already 10:40. I think I will stop here. I think you have most of the material for homework 1, maybe except the last part of problem 3. I will send out the clarification, right? Maybe you can save that part for the next week homework. Okay, I will stop here, right? So let me know if you have any questions, comments, email me. And if not, we will continue our discussion on thermal radiation next week. All right, thank you guys.
Thank you.
Thank you.
Thank you. Thanks.